Alrighty, folks, let's get started today. Today's image, so today in class, we're going to discuss a lot about what causes our seasons on Earth as we go through our course of our year and our orbit around the sun. We're very spoiled thanks to, satellites to now have a lot of beautiful images of the Earth. I always really like this one because it actually shows North America. There's a lot of different reasons. Of course, we care about the seasons. And of course, the reason seasons happen is an astronomical one. So it is important, and of course, a solar system class to discuss what exactly causes the seasons. So that's really our plan today. We're going to talk about why exactly the Earth has seasons. It has to do with the energy flux from our sun and the tilt of our planet. And we're going to do an activity to really drill down into these reasons. So first of all, this is going to be kind of random, but so Calvin and Hobbes, show of hands. Who's actually seen Calvin and Hobbes? Okay, so it still exists. There's actually a very good Calvin and Hobbes that discusses this. So, what causes the seasons? So Calvin's the little boy. The tiger is his imaginary stuffed animal friend. So Calvin says, since September, it's just been gotten colder and colder. I've noticed there's less daylight now. I've noticed now too. Oh no, this can only mean one thing. The sun is going out. In a few more months, Earth will be a dark and lifeless ball of ice. Hobbes, well, gee, I don't feel so bad about not setting up an IRA last year. So we're now going to discuss, explain to Calvin what exactly is happening. So first of all, though, I want you guys to recall from before the weekend what we were talking about for the orbit of the sun. So if you guys use your ABCD cards, can you guys tell me at which position in Earth's orbit does northern summer occur? We are closer to the sun in winter than we are in summer in the northern hemisphere. So we're actually going, as we are right now, closer to the sun, which also kind of makes sense because if you think about it, if there has to be a summer in the southern hemisphere, as we all know, and it was purely related to our distance to the sun, that wouldn't really make too much sense, right? Like, how would that work? We should then just have all summer all the time in one, our entire planet, not winter and summer. Here's another one. Yes, so if varying distance from the sun were responsible for seasons, could you get different seasons in Earth's two different hemispheres? So if it was purely to do with our distance from the sun, you would have the same seasons on the entire planet at the same time. It would not have a variation like we do now, where we are going into fall, and in Australia, they're going into spring. This also makes sense if you recall what we said last time in our lecture, where we were talking about the eccentricity of our Earth's orbit. And you can recall that I said that if you've had a mile as the equivalent, then the difference between the closest and furthest part of this Earth's orbit is about the equivalent of 8 inches. So 8 inches to a mile, that's really not big enough difference to have a huge effect on things. That's kind of the important thing to say here. So there was a second Calvin and Hobbes the day after the initial one where Calvin's worried about the sun going out. And Calvin says, Dad says the sun isn't going out. He says it's colder because the Earth's orbit is taking us further from the sun. He says winter will be here soon. Isn't it sad how some people's grip on their lives is so precarious that they'll embrace any preposterous delusion rather than face an occasional bleak truth? So this is actually, I think most people, if you go out and you're like, what causes the seasons? They'll say something like this because it's the orbit of the Earth. So, I mean, Calvin's dad was also wrong. Calvin is also wrong, where probably our sun is not currently going out as far as we can tell. But we're going to drill down into this. So then hopefully, if you ever encounter Calvin's dad in the future, then you can explain to him that they're both wrong. Anyway, so energy flux. What is really causing and driving our seasons is what a term called energy flux. Energy flux is defined as the amount of energy spread over an area. We define it with this symbol here. It is a Greek letter phi, and it is defined by, so it is equal to the amount of energy that you have divided by the area that that energy is going into. So with that, a higher flux of sunlight, so energy flux, we'll often just say flux instead of energy flux, a higher flux of sunlight hitting the surface of the Earth causes warmer temperatures. So that makes sense, right? If you have more energy in a given area going over a different area, a certain area, that's what causes us to have heat and light in our atmosphere. I mean, if we didn't have the sun, it would be basically a ball of ice on Earth. There's very tiny little geothermal events and things like that, but the sun is really what drives everything on our planet and allows us to live here. So the way to think of this is sunlight is going to shine through an area, which we're going to define as A naught, and that area is going to be at an angle theta from the horizontal surface, and it's going to illuminate an area that is going to be larger than this A naught. So the way to think of this is, so this is a sheet of paper, and here we have a piece of cardboard that we've cut a hole in. So let's say this hole is an inch squared or something like that, or 2.5 centimeters squared, whatever. So we have this, and we have our sunlight. If it comes straight down, it's going to be the exact same amount, but we also could have this theta angle. So, you know, the sun as it's setting is no longer straight overhead. So how are we going to account for that? We are going to have this additional term. So our flux is going to change. I'll show you guys visually what this means. So if our little cutout is directly overhead, so it's perpendicular, and the sun's rays are going straight down through it, you are going to have a square that is exactly as big as your cutout, so an inch squared or something like that. However, imagine now we're going to have an altitude. So we're going to have the angle of the sun is going to be high in the sky, but not exactly perpendicular. Let's say it's like over here, 70 degrees instead of 90 degrees. So when we've shifted our light and we're holding our sheet at the exact same spot, you're going to have a different projection onto the ground here. And then we could continue doing this, of course, because, you know, as the sun goes lower and lower in the sky, we're going to have an even different angle. So an even greater side angle, and we're going to have an even larger square. What you can see now, if I show you all three of these, the light incident at shallow angles illuminates larger areas, is what's the most important thing here. So as the sun goes from directly overhead more and more to the horizon, it's going to illuminate a larger area. What this means then, if we have this equation on the left, so flux equals energy over area, the energy flux at the surface of the table is going to be different at each of these locations. And that's because this area term has been changing. Even if the energy part has not been changing at all, the area part is. Does everybody understand this? Yep. Okay. So the next question is, if we are changing the area, as we just outlined above, will increasing the area make the flux? Thumbs up if you think it will increase, thumbs down if you think it will decrease. Yes, the energy area is going to decrease. So the way we say this is flux is proportional to 1 over area. So it is going to decrease over time as you have a greater and greater angle downward. So just to make sure we all are on the same page here, which sun altitude would result in the greatest energy flux? Where, to be clear, 0 is directly overhead, 90 is directly overhead and 0 is on the horizon. The answer is D. So 90 degrees straight overhead, it's proportional to the flux. So you're getting all the flux in the smallest concentration of area. So here. So if you're dividing by area and it's the smallest area, if this was, say, a 1 and this was a 10, you would then be dividing by only 1 versus dividing by 10. So now that we're talking about the sun and its altitude, there are several changes that happen, of course, due to the changes with time and latitude of the sun. So there are some practical impacts that have nothing to do with the seasons. So, for example, solar panel installation. If you're thinking about installing a solar panel, then the first thing they're going to ask you is like, you know, we're trying to get some on the roof of our house. What angle are you? What direction to the sun? If it's not worthwhile, then they're not going to install a solar panel. The second one is aspect-dependent vegetation. What I mean by this is if you go out into the mountains a lot of you guys are familiar with this idea that the plant life that you'll have, say, in the valley or even on some sides of mountaintops versus other sides of mountains will be different. And that is pretty much driven by the amount of sunlight that hits a certain area. Of course, when you get higher up, you also have rougher conditions. That's a different thing. But here you can see there's pines on this side and there's a boreal forest on this side. So there's different types of different amounts of sunlight hitting probably the northern side versus the southern side of this mountain pass. And that's what's causing us to have different vegetation. The third thing is avalanche safety. It's actually very important. So if people here like to do winter sports, you know, avalanches are on certain parts of mountains are much more common than other parts. So because basically when you have sunlight hitting a mountaintop with a certain amount of snow, it's much more likely to trigger an avalanche and have a slide, especially on those southern sides of mountains versus the northern sides. There's, of course, other things like, you know, if you're in a chute, that could be different, but the sun definitely matters, and the latitude the sun will reach also definitely matters. And finally, because this is astronomy class, one important thing here is the seasons. So we're going to discuss for a minute something called Earth's axial tilt. So we touched on this briefly already in this class, but the entire planet is not 0, 0 up and down. It's actually tilted about 23.5 degrees from the orbital plane. So our plane as we're going around. So if you imagine the Earth rotating like this, we're actually rotating around this 23.5 degree pole, not at a 0 degree pole, exactly perpendicular to the sun. So for Earth's axial tilt, this is kind of a fun practical question. We're pointed toward the North Star currently for our pole, for our 23.5 degree pole. So how many people here know how to find the Big Dipper in the sky? Okay, so a healthy amount. So the Big Dipper is basically in the northern part of the sky. In Oregon, it's up all year round. And you can use the Big Dipper to find the North Star. If you find the dipper part of the dipper, and you take these two stars right on the end of it, go up 1, 2, 3, 4, 5. There's a pretty bright star there, respectably bright star called Polaris, and that is the North Star. And so that's how you find the North Star in our sky. But you'll notice that I said for now. So this is a fun kind of longer term thing. So we always say, okay, the North Star is the North Star because that's what we orbit around. That's only for now. So this, on thousands of years timescales, our axis is actually wobbling at what star it's pointing at in the sky. So we are very lucky because currently we're within a degree of Polaris. We're within a degree. And it's 2100 roughly. So, you know, the end of the century that we're going to be the closest ever to Polaris. So it's pretty good right now for if you're lost in the woods kind of navigation. But it is worth noting that, you know, a couple thousand years from now, our descendants are not going to be able to use Polaris. And if you kind of look, we're kind of lucky that, you know, we currently have a pretty nice bright star in the northern hemisphere. If you go backwards, so 2000 BC, that's actually when the pyramids were constructed roughly. And so you can see that they had no North Star to know where true north was. They still figured it out, but if you read the ancient Egyptian records, they always talk about how you were looking at a point that was in, you know, this empty patch of sky, and they had a much more complicated way to triangulate to find north when you're thinking about all these ancient monuments that are lined up to true north. So I always think that's kind of a fun one to point out. I think a lot of people don't realize that the sky, in terms of things like the North Star and what we point at, that actually does change on not human lifetime scales, but on our human civilization timescales. It definitely does matter. I should also point out we're also lucky because the southern hemisphere actually has nothing at their south pole. So that's, as you can see, much more normal a situation. So we have this 23.5 degree tilt. And the ecliptic, which we talked about last week, traces out the sun's apparent path around the Earth. Due to Earth's axial tilt, the ecliptic is tilted from that celestial equator. So if we have the ecliptic here, it is about 23.5 degrees off. I'm going to show you guys an animation here. So here, for example, is our sun. Here is our Earth. here is our human who is standing at an arbitrary point on the Earth's surface. And now we are going to play a little animation, which you guys are going to use in this activity that's going to come up. So when you start the animation, you can see we're starting in February. So we're going to go in northern hemisphere into summer. Those sun's rays are getting pretty darn perpendicular. So it's pretty much directly overhead now. And then it's going to start even going past. If you're close enough to the equator, this is going to happen as well. So as we are going through, we are in now northern hemisphere summer and the dog days of summer. But we have passed June 21st, which is roughly the first day of summer. That's when the sun starts going further south again in terms of the area. You can see it's pretty much perpendicular again for the sun's altitude and is going to keep going down. Now it's pretty much where we are now in the season. And as we go toward December, this light is going to become lower and lower and lower in the sky, bringing on winter. So with that, so we have this line perpendicular to the ecliptic. We have our various seasons that the sun is running through, and that is what is causing our seasons here on Earth. So just to give some examples here, if we think of the Earth's axial tilt and the North Pole is tilted toward the sun, which is going to happen at one point of the orbit, the entire planet is then tilted about 23.5 degrees from that orbital plane. So what you're going to see is the sun's direct light is like this. A larger fraction, though, if we're thinking of where the equator is going into the northern hemisphere than the southern hemisphere. So what is this going to translate into? We have more direct light in the northern hemisphere, and that means it is summer in the northern hemisphere. Then, of course, we can think of the opposite. So we have now Earth on 6 months. It's going to be on the opposite side of its orbit. We have the same amount of sunlight coming from the sun. So there's the same amount of energy, except this time, if we think of the Earth in its tilt, we're only having a small fraction of that light coming in and hitting the Earth. It's a smaller area, so it's a lower flux than what we were seeing before. This means we have more direct light in the southern hemisphere, so it's going to be summer in the southern hemisphere. And then, of course, it is winter in the northern hemisphere. So then, of course, there's a natural point where neither pole is tilted toward the sun more than any other pole. So that is in March and September. So we have our ball here, exactly equal amounts of sunlight hitting both hemispheres. Then we have what is called the equinox, which is roughly March 20th or September 20th every year. It varies a little year to year. It's not perfect. So sometimes it's 21st, sometimes it's 20th, depending on your time zone, actually, is what it comes down to. So we're usually on the 20th side, not the 21st side of that date line. But so that's what we mean by the equinox. That means the first day of spring and winter. It's when both hemispheres of Earth are getting equal amounts of sunlight from the sun. So Earth's axial tilt in the southern summer, so the northern hemisphere winter. If we think about this part, the lowest part of the planet, that's called the Antarctic Circle, which is roughly 66 degrees south. So in southern summer, you have so much sunlight directed, and in fact, the sun goes so far, the sun never sets in the poles during the summertime. I'm sure a lot of you guys have heard that before. Similarly, the sun never rises when you're at the winter for that pole. So if you're thinking about where you want to go for the most amount of sunlight in that last question on December 21st, the answer is Antarctica, because the sun will literally never set all 24 hours. It will do a circle in the sky, but basically never cross the horizon. Similarly, if we thought of the northern summer, we have the Arctic Circle. And in the Arctic Circle, the sun never sets in the northern summer. I will say, so I've never crossed the Arctic Circle, but I've been to Iceland, which is about 64 degrees, so very, very close. you basically have perpetual twilight even when you're a few degrees because the sun never goes that far down the horizon. So you do definitely start having these effects when you start getting into the far Arctic or Antarctic. Finally, one thing I wanted to discuss very briefly with you guys is the Tropic of Cancer and Capricorn, which I'm sure you guys have heard of before. They're so called, by the way, the Tropic of Cancer and Capricorn because it has to do with the constellation the sun is in when it's directly overhead in that constellation. So the Tropic of Cancer is 23.4 degrees. And this is the furthest north the sun goes for when it is directly overhead. So 23.4 degrees north. It runs just south of Florida, basically, is where it is. And the Tropic of Cancer, so that's the furthest north the sun goes. It is actually in the constellation of Cancer when that happens. So that's why it's called the Tropic of Cancer. However, on the other side, of course, in the December solstice, this is the furthest south the sun goes in December, the Tropic of Capricorn, which is roughly 23.4 degrees south. Finally, at the equator, so it basically stays the same at the equator. It's roughly 12 hours daylight, 12 hours night every single day. If you ever go to the equator, basically the sun sets at 6 p.m. every day, and everybody knows that. I have a friend who grew up in Colombia, and he said that there it's basically if you have changes in temperature, it has to do with altitude because otherwise it's just the same weather every single day at the equator, regardless of what season it is, because the seasons don't really exist at the equator. As a quick wrap up, this map shows Earth's average surface temperature. So that's really what's causing the huge temperature gradients that you see between the Earth's equator and the poles. So yeah, these were the learning goals for class today. I'll see you guys Wednesday to discuss phases of the moon.